Hey folks, welcome to Advent of Code in F Sharp. We're at day 18 already, or at least it's the 18th of December. I have not caught up with all puzzles. I'm running a bit late, especially on the videos, but also on the puzzles. But we're steaming ahead here, so let's take a look at day 18. I have already peeked at day 18 while I was preparing my coffee, so what we have here is our input is a set of coordinates of 1 by 1 by 1 cubes on a grid, and they represent a droplet of lava, a single droplet modeled by 1 by 1 by 1 pixels, and we are supposed to calculate the surface area of this droplet. So whenever these two droplets or these two pixels touch, because they are adjacent on the x-axis, one of those sides is covered for each of the pixels. So we have 12 minus 2 equals 10 sides, and we have to do this for the whole droplet, so for the entire input set. I was noodling a bit around in my head, and I think we need very fast, or the operations we need to get very fast for today is checking whether a pixel exists or not, given a certain coordinate or a certain location. Checking for fast existence, that sounds like an array kind of thing for me. So I'm going to try to play around with 3D arrays today, 3D matrices. And yeah, let's see how far that goes. So I grabbed my input already, I grabbed the example here. Let's see if we can do something with array 3D. That's my plan, at least. So let me clear up everything. Sorry. So I don't think we're going to need much parsing here. I'm just gonna parse straight into array 3D. Will it work? Maybe that won't work. Let's quickly parse into tuples. So let's parse the example first. What is this? Just splitting on. Yeah, let's not use a regex. Let's just split on comma. Quick little parse here. There we go. And that's returning an array. So if we destructure the response, we should get x, y, and z, and semicolon. There we go. And then we can return the tuple. Is there a function that can do this? Something with 2, 3? No, 3 is too much. 2 would work. Okay, let's just return the tuple here. There we go. That's parsing. No, we need the integer values or the numeric values. Let's keep it in the integer space for now. Yeah, sure. That's better. That's something we can work with. So now let's build our 3D matrix. For array 2D, you have a helper function. I don't see it for array 3D. Interesting. What can we do with array 3D? We can initialize, we can create. Oh, there's an initializer function. That's actually perfect. We need the lengths. Yeah, that makes sense. The lengths are just the maximum x, y, and z coordinates. Yeah, okay. Let's calculate those first. So we're gonna try initializing an array 3D here. We need the maximum values for x, y, and z. And what are the minimum values? Can we drop negative? I'm gonna print everything out from the actual input just to see whether or not we have negative numbers. We don't. Okay, cool. So yeah, we need the maximum values here. Coordinates. Can you do first on a 3-element tuple? No, okay. X, Y, Z, and return X. That gives me the max X. Maybe we should just map first. So we map on the X coordinate and we take the maximum value. That should give us something at least. What are we expecting here? Let's see here. 2, 1, 3, 3. 2, 3. Yeah, okay. So we can do this for all 3 axes. We have X, Y, and Z, and over here we have X, Y, and Z. This gives us the dimensions of the matrix. 3, 3, 6. Are we expecting a 6 in here? Yes, we are. Okay, cool. Sounds legit. Then we need coordinates in our init function. And then we need an initializing function. I think we're going to store... Yeah, we're just going to store something in there. Let's make it a boolean. If we have it, it's true. Or if there is a coordinate, no. If there is a pixel that exists on that coordinate, we're going to hold it true in there. So how are we going to do that? We're going to look up the coords. If it contains X, Y, Z, yep, then we have it. So then it's true, otherwise it's false. There we go. So this should build our matrix. This should build our matrix, right? What is this thing called? I'm just gonna call it droplet. So that's our 3D array representing our droplet. Let's see if we can get something out there. Droplet. Just one sanity check, sorry. So we should have something at 224 and 223. I don't think we need the dot anymore. No, we don't. So yeah, there's something in there. And in 224, we have something. But in 227, there shouldn't be anything. It's even going out of bounds. That makes sense. We need to take care of the out of bounds thing. Okay, so I'm actually going to... Yeah, you know what? I'm actually going to declare a type for that. So a droplet is has the array 3D. Do I need to specify generics here? What's the type of array 3D? Bool array 3D, okay. No? The type is not defined. Oh, it's this thing? Yeah. So we have our model, but we should also take the bounds, the max size. Or no? Actually, our array 3D knows the max size. Never mind. Let's keep working with this. Cool. We have this. We can go out of bounds. We need to be able to figure out the neighbors of a pixel. So let's build a quick helper function for that. So neighbors for a pixel with X, Y, and Z coordinates should give us 1, 2, 3, 4, 5, 6 neighbors. One to the right, one to the left, one on top, one below. Right, that's X, that's Y, Z is the depth. Sure, let's. I don't think it matters that much. So we should have 6 neighbors. Let's try that with a origin. Looks correct. That was enough of a test for me. Whoa. Don't know what happened, but it's gone. I think we're done. If we now iterate over all coordinates or all pixels we know of, which is this thing. I'm gonna extract this in a function. Yeah, I'm gonna extract that in the function. So let build droplet given coordinates equals this beast. There we go. And let's drag our coordinates down. Let's have this function return something. And here are our coordinates, and here's our droplet. Build droplet given these coordinates. There we go. Now, we just need to count the number of orthogonally adjacent neighbors, and we can go out of bounds, but we'll see that in just a sec. So let's take a coordinate just to play around with it, and let's find its neighbors. And now we can ask the droplet whether or not this neighbor exists. If it exists, we have a neighbor. Yeah, that's the plan. So if this exists in droplet, we're gonna keep only those, and then we can count them. So let's build our exists function here that works on the droplet and a coordinate. Exists on the droplet and a coordinate, and it should return a boolean. Let's, if we have a negative if we have negative values here, we can give up. We're out of bounds. That's not supposed to be. So we're out of bounds. Otherwise, we can do some checking. Can do the same for. We can do the same for out of bounds and the maximum values, right? Well, how do I figure out the maximum values of an array 3D? Is it length, or there's these two concepts, length and base. Base is gone for 3D, so it better be length 1. It's giving me all the right numbers, so yeah. So I think we can do the same. So if x is bigger than what? Droplet, array 3D, length 1. And how are we doing with the off by 1 kind of errors? If my array 3D has length 3, what does that mean? It means that there's a 3 in there. So we can query for 3, we cannot query for a 4. Yeah, I should be looking at these max values actually. So our x value cannot be bigger. Let's start with that. If it's bigger, we have a problem, yeah. Same for y and z. And y is the second length in this array 3D thing, and z is the third one. And I'm hoping my auto formatter will clean it up. Yes, it is. It does. It looks better. And now we can just check whether or not our droplet at xyz contains a true or a false. Yeah, I think we're there. Coordinates 2, 2, 2. How many neighbors are we expecting here? 1, 2, 3, 4, 5, 6, 6, if I'm counting correctly. So it has neighbors and all. Oh no. Oh. We're off by 1. In the exists function, probably. Okay, so that was not correct. Interesting. Yeah, we're just calling exists once, so I know what this is. It's 2, 2, 2. 2, 2, 2 is definitely not smaller than 0. So we're trying to index, so we're actually falling into this case. Huh? What's happening with droplet? Why is it? Oh no, we're checking the neighbors, of course. We're not just calling exists once. Aha. Oh. Am I offsetting my indices incorrectly? Is there supposed to be a 0, 0, 0 in my head? Yeah, that should be no problem. What's happening? Nothing is happening. We're just encountering an out of bounds here. So let's think about it for a second. Let's print out the neighbor we're trying to check existence for. So we're checking this neighbor, and that is XYZ. What's happening? Why are you crashing? We're checking the first one already, so droplet should not have a 3, 2, 2. Yeah, we found our culprit. What's wrong with 3, 2, 2? It's actually literally in there. Huh? Huh? There's a 3, 2, 2 in our coordinates, yes. We're building the droplet given these coordinates, yes. Are we tripping up our X and Y values somewhere? What is the... What is the total space we're... I'm kind of guessing that maybe these values are not doing what we expect them to, so I'm gonna figure that out first. So max X, Y, and Z. Maybe it feels like the problem might be here. This looked like a very simple problem, but there we go. These off by 1 things always get to me. Yeah, so let's build our droplet again. Sorry, that was not what I was trying to see. I was trying to see, we know it's 336. I was interested about the coordinates our generator function receives. So yeah, that's the interesting part. Let's build our droplet again. What? Something went wrong, right? That can't be the case. That's better. So what are we seeing here? I'm not seeing any 3s actually. We are not seeing any 3s. So we are starting with an offset of 0, yeah. That is not a problem. No, too much coordinates is not as bad as not enough. But I'm seeing it run up until 225, and we know it's 326, so yeah, it wasn't off by 1. But I'm not gonna be offsetting. Am I going to be offsetting everything by 1? No, it makes no sense. We're just gonna ignore the zeros, but we are going to build our max x. We're gonna add 1. So max x or max c was 6. We're gonna make our array 3D 1 larger in all dimensions. So we'll have some extra empties in there, but I don't think for part 1 at least that matters. Or we'll see soon enough. So this probably is better. It's not crashing at least. And we have a droplet. Yeah, we have a droplet. So now we should get 6 neighbors. Let's have our computer counties for us. Do we have 6? We do. Cool. I think we found our bug. So yeah, I think we're done. Every pixel starts with 6 sides. We check how many neighbors it has. We deduct that from the 6 and we sum it up. So yeah, let's see. So we can map neighbors over it, and if we know the neighbors, we can yeah, let's take a smaller step here. So we have a coordinate. We check the neighbors given the exists function. Whoa. So exists in the droplet, and then we just need to count those. And we do 6 minus this whole beast. Now we're taking a huge step. And we just sum. And it's a one-liner. And if there's a bug, it won't be a one-liner for long. There we go. So what does this give us? A beautiful out-of-range exception. Yeah, this off by 1 thing is throwing us off again at the bounce check. Should we? Yeah, I'm not sure what the best approach is here. Should I change these bounds, or should I just not add an extra row and column? So length is 336. Wait, if length is 336. Oh yeah, I've made it 447. Oh jeez. So yeah, I think if we just decrease by 1, then our previous argument holds. Maybe this off by 1 thing is, or this extra row and column, I have a feeling it's gonna bite me in 10 minutes. But maybe it won't, so we'll see. 64 is correct. Cool. That's the surface of our droplet. Yeah, so let's grab our coordinates and our droplet here. Let's plop them in there. And let's do the same for input. We get a nice number. And that's correct. Yay us. Good to go for part 2. That looks like a very small and doable part 2. Great. I'm gonna do the old version control before I had version control trick and copy paste my file for part 2. That should still work. Ooh, it has not saved that I'm working on input. That's not too big of a deal. Okay, it still works. We still get 64. Let's move on to part 2 here. We are 25 minutes in. That's not too bad. Something seems off about your calculation. The cooling rate depends on the exterior surface area, but your calculation also included the surface area of air pockets. Okay, so that's a cool twist. Consider only cube sides that could be reached by the water and steam as the lava droplet tumbles into the pond. Steam will expand to reach as much as possible, completely displacing any air on the outside of the lava droplet, but never expanding diagonally. That's a very hard to parse sentence. Consider only cube sides that could be reached by the water. So that's the outside surface, yeah. The steam will expand to reach as much as possible, completely displacing any air on the outside of the lava droplet, but never expanding diagonally. Okay, so the outside side means you have to orthogonally, by moving orthogonally, you have to find a side of a cube. And if you can't reach a side of a cube that is exposed orthogonally, that means it's an inside. That's an inside side, so that's a cube of air, a pocket of air. So we have, what was it? Some 3,000 sides. We have some 3,000 sides, and some of them are exterior, some of them are purely interior air pockets. How do we figure this out? I'm gonna grab something to doodle with. I think the obvious hint is here. This steam thing. And it moves orthogonally. Doodle doodle. There we go. So say we have some kind of 2D cube. We'll extrapolate to 3D in a second. And all those sides are okay, but then we drop into the inside and there's some air pockets. Right now our approach is to go over every cube and see if we hit something. How do we detect closed surfaces or open surfaces? This steam and this expanding, it reminds me of a shortest path algorithm of Dijkstra, or a reachability algorithm. When someone taught it, Dijkstra to me, it was like buckets of paint and they creep very slowly. This is actually very similar. Can we do it with a reachability algorithm? We just drop some water somewhere, so let's make it blue instead of green. We drop some water and we say expand, and it creeps creeps, 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 wherever it can go orthogonally. And it'll go where it goes, and it'll stop when it has nowhere to go. I think actually that's a pretty cool way of looking at this problem. So how would that work? How would that work if we drop some water on the outer edges, or one single drop of water? What would happen? That's a very beautiful water droplet. So we hit something on the outside, and how do we know whether or not we can expand, or where we can expand to? We are not expanding to locations, we are expanding on edges or on surfaces of those coordinates. What is the actual... Okay, we need the surface area again, but only the external surface area, okay. No, this is too much of an ask on a Sunday morning. I'm going to at least need another coffee for this. And I'll have a noodle on this. So yeah, that's enough for today, or at least for this morning. Interesting twist though. I'm excited to dig into more. Cool. That's all I've got for today, or for tonight. I will see you again in a bit for part 2. So have a nice day, and see you later. Bye bye.